Now, this is the project where I was part of, I think I'm still part of it, but I'm not doing active research. That's why I want to introduce to you on stage Artis and Eduards, the two researchers who are dealing now with the wonderful world of Bluetooth protocol and Bluetooth implementation. With this, gentlemen, the floor is yours.
Okay. Hello, everyone. We will talk about exploration into Bluetooth radio frequency fingerprinting and protocol fuzzing. This is an ongoing research project, and we mainly deal with wearable Bluetooth devices and their privacy and security aspects. About us, my name is Artis Rušiņš. I'm a scientific assistant at EDI, Institute of Electronics and Computer Science, and I'm also a second-year PhD student at the University of Latvia.
And I'm a computer system analyst in ILab, Latvian University, and also second-year PhD student.
Yep. Okay, so first of all, agenda. We will talk about context and motivation. Why is Bluetooth interesting to us? Why are we researching it? Then we'll give a brief technical background. I will talk about gathering physical layer dataset and radio frequency fingerprinting. Then we will move up the stack from the physical layer up to protocol layers. Then we'll talk about fuzzing, and finally there will be a demonstration of Windows crash using Bluetooth. So, context and motivation. According to some statistics, in 2022, there were shipped 4.9 billion units of Bluetooth devices worldwide, and it's forecasted to reach 7.6 billion units in 2027, so a lot. I mean, we all, to some degree, use Bluetooth-enabled devices, and some of them are high power, some of them are low power, but the high power ones usually have privacy and surveillance risks because of the sensors on them. They collect data about location, about sensor data, about connection metadata, and etc. and etc. So there's a lot of these devices, and they contain sensitive data. So basically, that's why we are researching them. It is a complex protocol saddled with compatibility baggage because it was started by Ericsson when they started Bluetooth SIG, the group who develops Bluetooth standard in 1999. Yeah. And yeah, so all the versions are backwards compatible, starting from Bluetooth 2.0 to the most recent Bluetooth 5.3. So that brings a lot of luggage. And
there is also the part that they are sometimes hard or impossible to distribute updates because it's maybe it's not intended or space is not enough. Also existing quality assurance and certification does not test for malicious data, and firmware and driver may be able to circumvent device OS security.
Okay, so now I'll start my part, which is about Bluetooth privacy. So when I talk about privacy, I mainly talk about tracking individual persons, which is like a privacy risk. So basically, like, how do you start? I mean, you have Bluetooth devices, and how do you actually track people? So first idea is to use like what everyone knows, like when you open up your phone, in Bluetooth there is like a list of names. In Bluetooth standard, that's called user-friendly name, and this is usually changeable by the user, and if not by the user, then it's changeable by the device developer, and there can be multiple same names in one connection, basically. So that's not a reliable way of breaching one's privacy. Then there is MAC address, or in Bluetooth standard, it's called broadcast address, but it's the same. It's like Bluetooth SIG is aware of privacy risks, so that's why they exchange MAC address only once when you first pair the device, and after that, they continuously randomize this MAC address in the connection. So according to standard, every few minutes it changes. Like some cheaper devices actually don't do that, but most of them should. At least on the Bluetooth standard level, that is kind of solved because you cannot track people by their broadcast MAC addresses. But the thing we found interesting is that you can actually, according to some research, track people by the actual physical waveforms emitted by the antenna on your Bluetooth chip's PCB. because every radio transmitter has like, nothing's perfect. They have quantifiable unique features, which is basically a slight changes of the standard defined way of how communication should happen. For example, they should transmit at 2.4 gigahertz, but they transmit at 2.4 plus minus some hertz. And that's unique to different chips. And you can actually look at those differences, and maybe that way you can track people, because this cannot be changed at basically any level for user. So about the Bluetooth stack. Basically, what we are interested in here is that at the bottom we have controller, which is basically, this is the stuff that happens on Bluetooth chip, on the actual soldered chip on the plate. It does radio layer, baseband layer, link manager, protocol, etc. Basically, it does all the capturing of waveforms, demodulation, clock recovery for bit recovery, and then passes up to the host interface, which might be your phone's operating system or your, I don't know, laptop operating system. It passes up already interpreted bits because like, yeah, so basically I cannot get this radio information data, these unique characteristics of Bluetooth chips by using usual Bluetooth dongles, because the Bluetooth dongles will skip the bottom part and actually lift me up to the protocol layer. So what happens on the Bluetooth chip? It's your standard ISM band at 2.4 gigahertz, same as Wi-Fi, Zigbee, and some other devices. Bluetooth Classic uses 79 channels, each of 1 megahertz. Bluetooth Low Energy, 40 channels, each of 2 megahertz. What I want to emphasize is that Bluetooth Classic is not some old protocol nobody uses anymore. Actually, a lot of headphones uses that one for actual audio streaming, and the Bluetooth Low Energy is for more like sensor data, smartwatch data, etc. So it's still widely used. They use frequency hopping spread spectrum, which basically means that they transmit for very short times at one channel, then hop to another, and then to another, and it's like sort of hard to follow and sniff. So when you receive this data on physical layer, the chip does one more thing, and that's interpret packets into bits. So this is the Bluetooth Classic packet and Bluetooth Low Energy packet, and what we're basically interested in is identifiers. In Classic packet, in access code sync port, there is LAP, which means lower address part. That's the lower address part of MAC address, basically. This periodically changes, but it's still something you can find in like plain text. And for Bluetooth Low Energy, equivalent is the access address, also part of the full MAC address, or derived from it. So to summarize, we cannot reliably identify a device or track people by its user-friendly name, because that's changeable, and we cannot reliably identify a device by its broadcast address, because that changes all the time. But according to some research, we can try to identify a device by its radio frequency fingerprint. But we cannot capture physical layer radio frequency fingerprints using Bluetooth dongles, because that would lift us above the physical layer. So only tool basically, well, there are some others, but like most convenient tool to use to capture actual physical layer data is to use software-defined radios. We use USRPs and HackRFs. Like USRPs, especially higher-end models, can be up to 20,000 euros, but like if you're just starting and don't care about quality that much and are okay with not sniffing all the channels, you can use more accessible HackRF1, which is like, I think, 150 euros or something. So you buy your SDR, you hook it up to the computer, and then you download this beautiful software called InSpectrum, where you can visualize the radio frequency data. On the vertical axis, you have frequency, on horizontal time, and the color signifies the intensity. So basically, that's not working, okay.
Not working.
Yeah. But, okay, so basically these huge yellow lines on the lower part of spectrum, that's the Wi-Fi that's present nearly always everywhere. Even if your device it doesn't see the actual Wi-Fi name, the radio data is still there. It's just too weak, but it's it's messing with capturing our Bluetooth data. There are a lot of other Bluetooth packets. Actually, Bluetooth packets are those small ones which sort of climb a ladder on the diagonal way. At the beginning of the project, my colleagues actually went into the forest to be as far away as possible from any electrical devices around us, and they hooked up the SDR and tried to capture data. And even though your computer said it doesn't have anything around them, any Bluetooth devices, we could still see, like in the forest, like all of these kinds of packets which mess with us, because we cannot isolate our one device we're actually testing. We want to capture radio data from one device only. And the only way we could do this is by building a Faraday cage inside our lab. For those of you who don't know, that's basically a cage where nothing gets transmitted out. It's a huge metal box and nothing gets transmitted in. Yeah, it's a very quiet place. In our test setup, we previously used two USRP B210s, but now we switched to different model. We have Android smartphone, which acts as a master, because on Bluetooth devices you have to actually pair to something to get the data flowing and get the data exchange. We have our device under test. We have multiple wearable Bluetooth devices. And we even built a robot hand out of Arduino and servo motors, which basically presses the button when you, for a lot of devices, you actually have to press the button to start pairing process, right? And yeah, and you cannot do that into Faraday cage. Like, no normal person can fit in there. So we have to build a robot which actually presses the button, and we use some of that. And everything is optically decoupled, because a lot of USB wires can actually also act as antennas and pick up unwanted signals. So then we bought some wearable devices with this setup and actually recorded some data. So our data set consists of a lot of devices, and they all radio recordings follow a similar pattern. We first turn device under test in pairing mode. We close the Faraday cage so nothing else gets in. We start software-defined radio recording. We run, on the Android smartphone, we run Android debug bridge, which is basically a script which allows us to interface with Android's graphical user interface to press buttons. So, and with that, we turn on Android Bluetooth scanning. It connects to device under test. It exchanges data. For wireless headphones, we play a song, or for smartwatches, we interact with specific app to, I don't know, get a pulse reading or whatever. Then we turn off Android Bluetooth, and then we end the SDR recording and write metadata. So one experiment takes less than half a minute most times. Depends on application and what type of buttons we have to press, but it typically takes about 23, 25 gigabytes of data. We currently sit at 1.8 terabytes of data, and because we bought a lot of devices, we bought, according to Google Trends, most popular wearable devices and some other cheaper ones. We basically have a Bluetooth device radio recording data set in isolated environment, and with that we have metadata, which could be interesting to some other cybersecurity researchers, because we actually plan to publish this. There is radio parameters, there is event description, which means that there is pairing, advertising going on, and there's pairing, data exchange, disconnect, and everything is timestamped. So you can actually look at the timestamps in Spectrum and see, okay, this is when connection happened, this is when disconnection happened. Yeah, so, okay, we get these large isolated data sets, but we're still interested in individual waveforms of Bluetooth, because most of it's noise. Bluetooth doesn't stream continuously, it hops around frequencies, so most of it's just noise. And how do you extract that? So we used, at the beginning, we used GNU Radio and some of the, like, out of 3 modules for it. We modified software to our needs a bit, but it's mostly done in GNU Radio. We do energy detection, which basically means, like, we listen to a noise level, and when there's energy, like the wave goes up, we start extracting. Then we get the packet, but it's still at some different frequencies, so we have to multiply it by channel frequency, which is digital signal processing trick to get the packet at the baseband level. And then we save detected waveforms on disk. So this is how it actually looks like. On the left side, that's a regular Bluetooth packet, and on the right side, that's just a bit zoomed in. And you can actually see the sine wave it goes, and it's, since the Bluetooth uses FSK modulation, you can even demodulate it with eyeballing it, if you're, I don't know, experienced enough. So, fingerprints. I talked about that's like some unique features of transmitted waveforms. So, what actually is that? When we first look at this waveform, one thing, at least I immediately noticed, is that it does not oscillate about like around 0. There is some offset. That's called carrier frequency offset. That's the frequency deviation from standard defined way of doing things. It's small enough so devices still work, but it's there. It's a defect, and you can measure that and subtract it, and now you have corrected packet. We do this for all waveforms. We take this one number, which is carrier frequency offset from 0, and save that. Next fingerprint is what we call the scaling factor, which basically means it's a function of deviations in amplitude variation, because since the Bluetooth is FSK modulated, there'll be no variations in amplitude, but there is. And we captured that, and we also save this scaling factor number to disk. This is when the scaling factor is applied, which basically corrects the packet, but we don't really care about that. So we do that for all of the packets. For all the data set, we extract packets. We collect carrier frequency offset scaling factor from each of the devices, and then just plotted them on scatterplot and see what happens. On the horizontal axis, we have carrier frequency offset. On the vertical, scaling factor. So each different colored point is different device. And each device is like radio chipset generated different fingerprints. And this is exactly what we wanted to achieve, like without relying on information on higher levels, without actually decoding packets and looking what's inside of them. We could, I could later look at this picture and tell you exactly what these device waveforms were from. To put it into like a numerical analysis or something like that, we performed the k-nearest neighbors classification. So in ideal conditions, we achieved 97% of accuracy. Like I think out of these, like the Xiaomi Mi Band was only one that was a bit confusing or close to another clusters. But this is not the first time I talk about this, and people most of the time ask, okay, you got this data set and you've done your work in isolated environment, but what about the real life? What is it feasible actually when there's a lot of devices around? And so I wanted to show you how that actually looks. I will use HackerF with the modified Bluetooth sniffer. This Bluetooth sniffer, it's actually kind of new software, and it was presented in last year's DEF CON by Mike Ryan. I actually took this software and added some code to it to extract fingerprints. I will show you individual waveforms, and I'll try to show fingerprints of that captured data. Can I make font bigger?
You can zoom in if possible.
Yeah, I don't know how. Yeah, sorry about that. Okay, first of all, I'm going to sniff some Bluetooth packets. Hope it works. Oh, I'm actually using HackerF1, so this is actual Bluetooth packets here, transmitted in the air. Oh, no. Okay, so there's a lot of packets. So basically, each of these lines, this is when the enough energy is detected that packet could be there. And this is when there is LAP or AA. LAP, I remind you, it's a lower address part. It's when the actual packet is received. It's passed the check. It has the correct headers, correct barker codes, correct synchronization phrases, etc. That's a valid Bluetooth packet here. So yeah, I captured these. So, and what we can see here, this is your regular Bluetooth packet. We get the timestamp when it's captured. We have carrier frequency offset. We have scaling factor for each of these packets. This is for you to just visualization, just how regular Bluetooth packet looks like. We have packet bit count, what's inside. We have actual bits inside in hexadecimal format, and we have lower address part of it extracted. You can extract way more things out of these, like header information, etc. But yeah, I just extracted the lower address part. Another thing we can do is to actually look at this in real time. So this is how packets I just captured changes their scaling factor in each time and their identifiers. So basically, I could sit here and look at my dataset I recorded previously and see if any of those devices I previously recorded in isolated environment pops up in this case. And that way I can see, okay, this device is present. So that's that. Full screen.
It's not very full screen, but it's
okay. So
better.
For this is just a demo. It's a start, like just a raw demo. There are some rough edges, but basically, obviously, we have privacy issues with this because you can actually track people with this. One other potential use case is secure facilities. Can we detect untrustworthy devices, like equipped with a database of our recorded fingerprints? We could actually test the device and see, okay, this device typically has this kind of radio frequency data set, and it typically in the advertising says that, okay, I am Samsung smartwatch. But if the fingerprint doesn't match the smartwatch, we can actually mark it as potentially malicious. One other potential use case we came up with is targeted cyber attack, because some Bluetooth exploits and cyber attacks don't work on all Bluetooth devices, on all Bluetooth versions, etc., etc. But if we can split this up, we can, by fingerprints, we can narrow down the actual device we are attacking. So we get a targeted attack. Yeah, and yeah, I'll give word to Eduards.
Okay, and now we are moving up the stack. Bluetooth stack consists of several layers. I don't know if you can see this, but we are like we were here, radio layer, and now we're going up baseband layer, link manager protocol, and above this is like firmware, and above there is a software part, and here is a logical link control and adaptation protocol. We'll talk about this, and there are two tools that we were looking at that we also will test a bit later. Okay. There are many chip vendors, and each of them provides its own implementation. That's good because we can choose from them, but mostly they are closed sourced, and we cannot know how they did this, and if they held to the specifications and did everything right. So out of the 30 implementation tested, 25 had some bug. And it was detected using fuzzing. So, and what is the fuzzing? Fuzzing is like a testing method. We can imagine it like we are throwing a ball and see if the system can catch it. But we cannot throw a ball randomly. It's like a puzzle. You have to throw the ball in the right section, in the right way. If we are doing that completely randomly, the test will not go through, and the state of the system will disrupt, and we will not detect the vulnerability that is there. So, and the usual goal of the fuzzing or outcome is that our device will crash, will deadlock, restart, or something like that. So, there are 5 usual errors that we can detect using fuzzing: memory corruption, implementation faults, denial of service, disclosure, and we can also find something that is there but is not documented because of the manufacturer, or because it is like the hidden function, information gathering, or something like that. So there are 2 dynamic fuzzing approaches. One is like you are collecting data in the real time, you are monitoring and debugging. Another one is emulation. You emulate the whole device and run in your sandbox and see what's going on. So, and now about those tools I mentioned before. One is L2Fuzz. It's a Python script, basically, that is aimed at upper layer, like for the driver testing, and it may crash your device drivers. And other one is a Bracktooth. It's a bit older, but it's still used in automotive industry and audio device testing. And it's aimed below, just for the firmware, link manager protocols, and it is using also the emulation part and also this instrumentation. Both approaches. So about demo, I'll try to do that. We have like a script, some scripts to demonstrate, and all right. It's like very, very small. Sorry. Maybe you can help. Oh, yeah, I see. So, what we will try to do is to run a script. What's happening now? I just read the database of the Bluetooth addresses that I previously recorded using another tool, so it is easy for me to test. And I will try to. Here is like WinMac Air, and this is this computer. I will try to just crash it. I hope it will happen, but it's not guaranteed because the fuzz data is every time is different, and you may or you may not crash it, but I will try. To be sure. Oh, okay. It maybe crashing, maybe not. So it's device 11. There are 4 options. I can launch Bractus exploits, launch Bractus fuzzer, launch crash Windows, that it will do. And the 4th option is find profiles that this device offers, also for the fuzzing. And so I'll try the 3rd one. Something's not going right. 11. 3rd. Okay. A bit time. Device is up. Device is up.
While we're waiting, this is this KP in the background doing the based on this KP the L2 fuzz, right?
Yes.
So it's using this KP to run the fuzzing as well, or do you automate somehow the fuzzing, or this is just you allow this KP to do all the things, the L2 fuzz?
I modified L2 fuzz tool to just do the thing that most likely will crash Windows. I just stripped all those parts that doesn't do that and try to make it, how to say, faster. No, this time I think it's not going to do. I have also the video. I can demonstrate where it's successful. The same thing happens. So I will show to you. Like you can see the TP-Link Bluetooth adapter that is plugged in. It's also here, and we are starting like showing that it's here. Checking Windows. We're up to date, and then we are launching the same attack. You've already seen that. I just input the address. Also launch attack. And why it's not happening every time? Because the data, the fuzz data is somewhat randomly generated, and it's possible that the crash will not happen. And each time the device generates some error code that is not like before. It's unique, somewhat. I have seen 4 or 5 different error codes like this. This time it didn't happen, but you know, I have the backup. So, and it will show you the crashed packet after it will finish. So it might be repeatable. It's not easily repeatable because I cannot like just send this one. I have to write my own stuff to do this. So I can also improve this in the future. So let's get rid of this and continue. So yeah, crashes. I don't know if you can see. There's the error codes I encountered, page fault in on-page area, invalid memory access, basically system thread exception not handled. That's it's like for the remote control driver that is allowing me to start audio of the device. It's also crashing. The third one is VDF violation. It's like crashing USB 3 controller in which the device is plugged in. So basically everything is crashing. And last one is driver IRQL not less or equal. And that's caused by Calper driver. So, and what to do to not get get crushed by your neighbor or something like that? You should think about which devices should be allowed in your institution, make inventories. Also make sure that you don't pair the devices in unsafe places like IT stores or some help desk with many other people around. Also, the hidden profiles is not the best idea. Better is just turn off the Bluetooth if you don't use it. And also update, because updates goes a long way. It helps, it fixes the things, and that you should do. So here are the references, and if you have questions, you can also write us and see our profiles. So.
Okay, thank you.
Perfect. Before I open the questions from the audience here, I have one question to each of you. So, because Artis, you were dealing with the fingerprinting, and now regarding the fingerprinting, you mentioned that you can track a particular user. My question may be to more narrow it down. Can you actually track a particular person because the device is emitting a very unique fingerprint, or that unique fingerprint is across all the set of those particular devices? Yeah. And if there are multiple, well, if there's only one person with that unique device, then it can be...
Yeah, I understand your question. It's basically what exactly are we fingerprinting, right? But we had this idea also to, okay, are we fingerprinting the Bluetooth device, the Bluetooth chipset, the manufacturer, or the, I don't know, the PCB antenna or whatever. But to answer fully, we don't have enough data yet, because you would actually need to test multiple of the same devices. But to do some quick tests, we bought some cheap Amazon headsets, like 5 same ones. And actually what we found out that 3 of them had identical fingerprints, but 2 of them were separate. So we could actually, for some devices, we can actually separate between sort of same devices, but I don't know, that's manufacturing process or different kind of box they've taken it, but yeah, we could distinguish between same devices basically.
Right, that would be interesting if the same model would be varies the fingerprint, maybe because maybe some other component is changed or something like this. Now, thank you. Coming down to Eduards. Eduards, you were dealing with fuzzing primarily. Now, the challenge I think is the primary fuzzing with the fuzzing is to identify if the target device under the test is crashed or not. So you're pretty much limited with only one check, ping the device, or I don't know, see if it responds. Or are there any other ways that you figured out how to identify if your test case has resulted in crashing the device or triggering unexpected behavior?
If I'm fuzzing through the airwaves, then I have no way to actually tell if the device is crashed other than I see it myself. If I do the emulation stuff, then it's a bit better because it's in my control. If I test like Bluetooth headphones, there is no way to tell if maybe the battery is depleted, or maybe it just crashed because it's like not because of me, but because of something I pressed. I don't know. Sometimes these headphones are so poorly built that they just crash by themselves, you know. So it's not very, very precise science, but you can tell if you play the music and you launch this attack and you can hear like some disruptions in audio when you are fuzzing, then you know it's you that's doing it.
Right. I understand. That's the same problem that I've faced when dealing with fuzzing network protocols, but not on the wire, but not on the wireless. Let's take questions from the audience as well. If there are any, just raise your hand. All right. Oh yeah, there is one question there.
Crashing device sounds sexy for the lab, but is there a potential that you can make device behave in a different way, just crashing, like gaining control over it or making it execute some code or something. Are there chances for that?
Not through the fuzzing. Fuzzing is just like to detect vulnerabilities that are not yet detected. You can find new exploits, and if you find that one exploit that allows you to do that, then you can, but it's not the direct result. It's like afterwards. You just find a new zero-day vulnerability by fuzzing, and then you develop your tool to get control. It's on a later, for the later.
Thanks.
Okay, there's one more.
Hello, and thanks for your presentation. It's a great thing that someone is doing fuzzing related to Bluetooth. I used to work in a company which did it in commercially also, and one of the tools were related to the Bluetooth. Back in the day, everything basically crashed and were in poor condition. So that's about that. So great to hear that that's continuing. Quick comment on the previous question that with the fuzzing, I think you can just find the bug, and sometimes those bugs are vulnerabilities which lead you to continue to the exploitation. I just wanted to comment a bit about the challenges when you are doing the fuzzing. I think the one good way is someone else is considering doing some fuzzing is that you try to do valid queries after every fuzzed packet or so. So you have some valid case that if I send this package, I should receive that kind of package. And you do it like every other request is like a valid, not fuzzed case. And that way you can validate that if the system where you are fuzzing is still functional. This is not always possible, but if it is possible, if you can validate it, that's an easy way to automate it and keep it and leave it running and let the computer do the monitoring.
That's a good point, yeah. I agree.
Thanks.
Yeah. Thank you.
All right, from my perspective, this is the question to you guys as well, and because I've been part of the project for a while. I think the value in this is also, if you can fingerprint a particular device, you can pretty much identify what kind of vulnerabilities you can match against this. So there might be a potential where you find a vulnerable device, either you do not allow it to go through the gate, security gate, or you can launch a vulnerability exploitation. Or there are any other kind of synergies there between the two?
Not sure, actually. These are the 3 use cases we've actually been focusing on the most. But one thing I can comment on about, like Eduard's approach with the fuzzing, is that you saw in the terminal that he actually got the full MAC addresses, right? And the question arises, can we actually track people by the full MAC addresses? And we can. But the thing with his approach, I don't think Eduards mentioned it, he uses the Bluetooth dongle. And that's a sort of active approach, because when you discover devices, they're actively sending packets out.
Correct.
My approach is 100% passive.
Yeah, that's correct. All right, with this, let's thank the speakers again.